Hello class, and welcome to section 7.4, which is about factoring polynomials. By the end of today's lesson, you will be able to find the greatest common factor, and you will be able to use that GCF as well as reverse distribution to find factorizations. So a quick reminder, GCF is the largest thing that can divide a pair or a group of numbers. In this case, our GCF is going to be a monomial. So it might be a singular number, it might be a singular variable, or it might be a combination of numbers and variables. But we're going to be able to take that factor out of the other pieces within a certain group. So, finding a GCF. So we've got 48g to the fourth h and 64g to the third h squared. So our first priority, since we have numbers and variables, is we're going to look at the numbers. The easiest way to do the numbers to ensure that you have the actual greatest factor is to quickly list out the factors of each number. You can either do this on paper or do it mentally if you are able to do so. So for 48, it's 1 times 48, 2 times 24, 3 times 16, 4 times 12, and 6 times 8. So we have those different factors. Over on the other side, we've got 64. So that's 1 and 64, 2 and 32, 4 and 16, and 8 and 8. So those are all of the possible GCFs that we could have. Now looking at your two-factor list, you want to pick out the biggest number that shows up on both lists. In this case, the biggest number that shows up on both lists is going to be 16. So the number part of my GCF is going to be 16. Then if I write these variables out, g to the fourth means g, 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 and then I've got an h. And on the other one, I've got 3 g's and then 2 h's. So we're looking for the greatest common factor, the things that they have in common. So if we're looking at this, there's 3 g's over here, and I can pull out 3 g's over here. So that gives me g to the third for the g variable. And then I can pull out 1 h from each monomial for the other part. Another shortcut that you can do when you're looking at the variables. So we've got g to the fourth and g to the third. Your GCF is going to be the lower exponent. So in this case, that g to the third. Same rule applies, h and h squared. My lower exponent is just 1 or just plain old h, and that's what I pull out for my GCF. Go ahead and try this one on your own. So again, we make our factor list. We pick out the biggest number, which in this case is 6. Looking at our exponents, we've got a singular for our factor, b squared being the smaller exponent, and then c doesn't occur in the second monomial, so it cannot be part of our GCF. So now that we understand the concept of GCF, we're going to use it to help us factor. When we factor, we always want to pull out the GCF. So I'm going to look at all of these, and I've got 15, which is going to be 1 and 15, 3 and 5. I've got 20, which is 1 and 20. 2 and 10, 4 and 5, and then I've got 35, which is 1 and 35, 5 and 7. Again, you do not have to write these factors out. If you are able to pick this information out without writing it down, writing it down is not a necessary step. So we can go through and find out all of them can be divided by 5. H only occurs in one of my 3 terms, so that's not part of my GCF. I've got an m to the second, an m, and an m. So I'm going to have a 5 and an m, and then n only occurs in that middle term. So I've got 5m as my GCF. Now, when I factor, the rest of the expression becomes what is left over. So if I have 15 and I take out a 5, that leaves me with 3 left over. I didn't take out an h, so that's still there. And of my m to the second, I took out 1m, so that means 1m is still on the inside term. Then I'm going to jump to the next piece. Plus 20, pull out a 5, that leaves me a 4 left over. I pulled out the m, so that's gone, leaving me with just the n. And then I subtract 35, take out the 5, is 7, m, and m. There's nothing left there. So my factored form is 5 times 3hm plus 4n minus 7. So we pull the GCF out, and the remaining pieces, once that GCF is factored out, go inside the parentheses. If you have something where you have a negative leading coefficient, so that first number is negative, we always want to make sure we pull that out. So when you are finding the GCF, you're going to find the number as you normally would, and then you're going to add a negative to it. So factors of 4, 1 and 4, 2 and 2, 8, 1 and 8, 2 and 4, and 2 is just 1 and 2, giving us our GCF of 2. But in this case, since we've got that leading coefficient, that negative 4 in the front, we are going to pull out a negative 2 as our factor. So again, if there is a negative leading coefficient, find your GCF number normally and then turn it negative. Then we've got to deal with our variables. I've got a squared, a and a, so I can pull out a singular a. I've got b, b squared, and b, so I have a singular b to pull out. Then I'm going to go through and I'm going to have the rest of my factors. So negative 4 divided by negative 2 gives me a 2. I had 2 a's, I pulled out 1, which leaves me with 1 over. Had a b, pulled it out, nothing else there. Then I've got a negative 8 divided by a negative 2, turning that to a positive 4. And then we've got a, that matches up, b squared, pulled out 1b, so we have that there. Then I've got 2 divided by a negative 2, giving me a negative 1. A and b already taken out. One thing I forgot to mention on the previous slide, this is thought of as reverse distributive property. Instead of drawing that rainbow to factor it into a polynomial, we're trying to pull the thing to the outside. So one quick way, if you want to quick mentally double check your work, you can use the distributive property to check, and you should end up back at that original term. Last case that you could run into, we've got 17cd to the 4th plus 4c to the 3rd minus 12d squared. So I start by looking at my numbers. I've got 1 and 17, that's the only factor there. 4 is 1 and 4, 2 and 2. 12 is 1 and 12, 2 and 6, 3 and 4. So my biggest term for number, that can be factored out as a 1. Then I've got c to the 3rd, and nothing, so I can't pull out a c. I've got d to the 4th, nothing, and d squared, so I can't pull out a d. When you get to a case where if 1 is the only factor that you have, we actually call this expression prime, or it might say already factored, or it might say the only factor is 1. Either way, what this means is we cannot simplify this anymore. We cannot take a GCF out. This is the only thing that we can do. It's as simple as it gets. Go ahead and try this one on your own. Line up your factors. You find that the GCF number is 9. You can take a y out of each one, and you end up with 9y parentheses 3y plus 2. We're going to apply this idea to a couple different area problems. So we're looking for the missing side lengths of these rectangles. It's telling you that the area of this smaller rectangle is 14g squared h4, and the larger rectangle is 35g h to the 5th. Now, if you notice, the width of these rectangles are going to be the same. So if you're doing any problems with area, your GCF is going to be the measurement that is the same on both objects. In this case, it's our width or that height value. So our job is to figure out the GCF. So our x being the GCF, we're going to look at our numbers. I've got my factors of 1 and 14, 2 and 7, and then on the opposite side, I've got 1 and 35, and 5 and 7. So I end up with that common factor of 7 for both of them. So 7, g squared and g, lower exponent is 1, h to the fourth, h to the fifth, lower exponent is h to the fourth. So that width value then is 7gh to the fourth. Then our other measurements are going to be what would be left over in that parentheses if we were writing it out the long way. So 14, I took out a 7, dividing by 7 gives me 2. G squared, take out a g, leaves me with 1 left over. 4 h's, take 4 out. So I'm left with y is equal to 2g. And then for the z factor, I've got 35 divided by 7, which is 5. I had a g, I pulled it out. And then I had 5 h's and pulled out 4. So I'm left with 5h. Go ahead and try this one on your own. Factoring out, our GCF number is 12, and then we end up with a, b, c squared, and then you use those factors or use that singular factor to figure out the remaining 2 pieces. Last thing you might see is it might ask you for the area of a particular shaded figure. So in this case, we're looking for this pink area. We have a circle. Our radius is 8, which means that we can go ahead and figure out the side length of our rectangle. So this part is 8y, which means the other radius is also 8y. So the side of my square is going to be equal to 16y. So then I'm going to next figure out the area of that square. So in order to find area, we need to take our side and square it. So 16 squared is going to give me 256, and then y squared. So that deals with the large pink square. But we only want the shaded part. So now I need to be able to take out the area of that circle. So the circle area is going to be pi times my radius squared. So 8 squared gives me 64, y squared, and then multiply that by pi. Now, in order to figure out the shaded area, I'm going to go ahead and take my original area of the square, which is going to be 256, 256 y squared, and subtract off that circular area. So now I would go through and I would list out both of my factors. When I list those out, you would find that both of them are divisible by 64. That's our biggest number. So our shaded area in factored form is going to give you 64 y squared and y squared, so I can pull that out. And I can't pull out pi because that's only in the second term. So that's going to leave me with 4 minus pi as my shaded area, that pink part in between each little corner. Go ahead and try this one on your own. Again, solve for the side, find the area of the square, find the area of the circle, and subtract. If you have questions about this or anything else from the lesson, please let me know when you get to class.